We shall be talking about electricity and magnetism. And let me begin by talking about what the Greeks have done in studying electricity and magnetism. Now, I have to make clear that to the Greeks, these were exotic phenomena. They had nothing to do with life or with anything practical. They were curiosities. However, what we will learn in the course of today's talk is that electricity and magnetism are fundamental, that we are creatures of electricity and magnetism, of electromagnetism, that everything we see, everything we feel, everything we hear, everything we taste, everything we touch, everything we do is electromagnetic. Gravity is important, yes. It keeps our feet to the ground and our seas where water should be and our atmosphere about us. But we don't really need gravity. We can live in space, and astronauts live in space without any gravity. But we do need electromagnetism. We are electromagnetic. Now to the Greeks. They gave us the words electricity, and they gave us the word magnetism. Electricity comes from electrum. Electrum, or Electra, is a girl's name. Electrum means amber, and a girl with hair of a certain color is called amber, and this material is called amber. And when you take a piece of amber and rub it with fur, it will make sparks. It becomes electrified. And so the word electricity comes historically from the original source of electricity that the Greeks played with, frictional electricity, what you get by rubbing a piece of amber or resin with a piece of fur. They also noticed that there's a different kind of electricity. That resinous electricity is what you get when you rub a piece of resin. Vitreous electricity is what you get when you rub a piece of glass or glass-like material. And there were two electricities, and the Greeks noticed that things with the same kind of electricity would repel one another, and things with the opposite kind of electricity would attract one another. And they played little games with electrical phenomena, not realizing that electricity is such an important part of our world. They also played with magnetism. How did they do that? They found natural magnets, what we call lodestones, lying around in a certain part of Greece, and that part of Greece was called Magnesia. And that's the origin of the word magnet, from the particular region of Greece where natural magnets were found. And they found that natural magnets would attract pieces of iron, and that magnets had two poles, a so-called North Pole and a South Pole, and that similar poles would repel one another and opposite poles would attract. And thus they gave us these notions of electricity and magnetism, just as curiosities that had nothing to do with the real problems of science. They were just fun, as they were for me when I was a kid, and I had a little electrical and magnetic set, and I could duplicate the experiments that the ancient Greeks had done for fun.
La storia dei fenomeni elettrici, che vede protagonisti grandi personaggi come Ampère, Faraday e Maxwell, parte dai laboratori dei fisici e finisce nelle nostre case, nelle incalcolabili trasformazioni che le loro scoperte hanno portato nella quotidianità della vita moderna. Oggi immaginare il nostro mondo senza elettricità è come pensarlo senza l'aria per respirare. L'intero sistema di vita di gran parte del nostro pianeta collasserebbe in un istante. Blocco dei sistemi di produzione industriale e degli strumenti per l'erogazione dei servizi più vari, ma anche dei semafori per regolare il traffico, dei bancomat, dei telefoni, dei personal computer e di tutti i cervelli elettronici che regolano sofisticati e complessi processi di interesse collettivo. E nelle case niente illuminazione, niente riscaldamento, niente frigorifero, niente musica, niente TV. Gli ospedali si fermerebbero. I malati che dipendono da macchinari per la loro sopravvivenza vedrebbero ridursi drasticamente le loro aspettative di vita. I trasporti tornerebbero ad affidarsi agli animali. Gli stessi approvvigionamenti alimentari sarebbero messi a dura prova. Sembra fantascienza, eppure i paesi sviluppati si trovano oggi a dover ridurre gli sprechi energetici per poter sostenere proprio il sistema di vita che l'elettricità ha messo in movimento. Un mondo senza elettricità, dunque, non è più neppure pensabile. Eppure, questo straordinario cambiamento è avvenuto nel corso dei secoli grazie alla curiosità di qualcuno che giocava sfregando una bacchetta di ambra.
Nothing much happened for the next 1,000 years or so. The curiosities were written up and forgotten and then rediscovered perhaps by the Arabs until finally in 1600, a man by the name of William Gilbert. Now, what did Gilbert do? Gilbert realized, learned what the Greeks had done and continued doing experiments and pointed out the similarities between electricity and magnetism and also the differences between electricity and magnetism. For electricity, anything could be electrified. You take a piece of stuff and you rub it and you will make electricity. When you walk on the carpet and then touch a radiator or touch an electrical switch on the wall, there'll be a spark. Electricity was made by the leather of your shoes rubbing against the rug. So electricity is easily produced by friction, and anything can carry this electricity. Whereas magnetism was limited to iron. If you had a natural magnet and you rubbed it against a piece of iron, that iron would become magnetized. And iron needles, as the Chinese had shown, floating in water, would point north, would point, one of their side of the needle would point in, toward the north, the other side of the needle to the south. Gilbert knew that the Chinese had discovered the compass. Gilbert knew that compasses had been used in the Age of Discovery when intrepid Spanish and Portuguese and British sailors were discovering the nature of our world. So he compared electricity and magnetism. There were similarities. In the case of electricity, there were two kinds of electricity. Similar kinds of electricity repelled one another. Opposite kinds of electricity attracted. So also in magnetism, similar kinds of magnetism, north poles repelled one another. Opposite types of magnetism, a north pole and a south pole, attracted one another. Though Gilbert demonstrated that there were similarities between electricity and magnetism, and there were differences. The similarities were that there were two kinds of electricity, vitreous and resonance. There were two kinds of magnetism, north poles and south poles. That's a similarity. A difference is you could separate one kind of electricity from the other kind of electricity. You can have an object charged one way or charged the other way. On the other hand, a magnet had a north pole and a south pole. The magnetic compass, which the Chinese had discovered, would have a north pole, which would point to the north. It was called a north-seeking pole. And of course, the opposite pole would be attracted to the south. But every magnet had two poles. If you take a magnet and break it apart, you're trying to separate the north pole from the south pole, you don't succeed. You end up with two smaller magnets, each of which has a north pole and a south pole. Very different from electricity. In addition, Gilbert realized, he addressed the problem of why does a magnet point to the North Pole? Why does the north-seeking pole of a Chinese magnetic compass point north? And he said, the only way is if there's a big magnet inside the Earth. And so he was the first person to speculate, and he was correct in this, that there is a big magnet lying within the Earth. The other essential feature is communicability, that you can communicate magnetism from a lodestone to a piece of iron, but only to iron. But you could communicate electricity from one object to any other object. And that was the beginning of the science of electricity and magnetism. By the 1700s, people have learned to do interesting electrical experiments. They were able to make electrical effects with very ingenious devices based on friction. Things would rub against other things in a circular device that was powered by moving your hand on a generator. And you could make big sparks, you could make electrical effects. And lots of people in Europe were trying to understand the detailed properties of this fascinating electricity. Ben Franklin, for example, the American patriot, one of the founders of the United States of America, was an ardent investigator of electricity. And he did some of the most dangerous experiments. He flew a kite with a conducting wire and showed that during thunderstorms, when there's thunder in the sky, when there's lightning, electricity passes through the wire and produces sparks on Earth. And this was a very dangerous experiment. The discovery that lightning is an electrical phenomenon cost his colleague, a Russian who did the experiment at the same time, his life. The Russian scientist was killed in doing this very same experiment. Franklin invented lightning rods, which protected houses from lightning. And he did something else which was fabulously important. Remember, I told you there were two kinds of electricity. One kind you got by rubbing a piece of glass with a piece of silk. The other kind you got by rubbing a piece of amber with a piece of fur. One was called vitreous. The other was called resinous electricity. It was thought that there were two kinds of mysterious electrical fluids, but Franklin made the brilliant observation that you only need one electrical fluid. And one kind of electricity is when you have too much of this fluid, the other when you have too little. So one kind of electricity is called positive, the other kind of electricity is called negative. And that sort of simplified the analysis of electricity. The next thing to happen involved an English physicist named Priestley. Priestley was one of the discoverers of oxygen, and that's another story which we're not going to talk about. He was also a student of Newton. He studied Newton's work, and he knew that gravity has a very funny effect, that if you have a hollow shell, if you dig a hole deep in the earth, you don't feel the gravity of the material outside of you. And he noticed that the very same thing happens when you electrify a cup or a bottle, that there's no electrical effect inside the cup or the bottle. This was brought to his attention by Ben Franklin, in fact. And Priestley concluded that the only way this can happen is if the electrical force is in a way very similar to the gravitational force, that it satisfies an inverse square law. Now he never followed up this brilliant observation. And at roughly the same time, just a few years later in France, Mr. Coulomb, using an electrical machine, also decided to investigate the electrical force that two charged bodies exert on one another. We knew that things with the same charge repelled one another, things with opposite charge attract one another, and Coulomb showed that there is a precise formula governing this force, that the size of the force between two charged objects depends on the size of either charge, the product of the two charges, and it falls off with the square of the distance between. So if you have two charges 1 centimeter apart, the force will be 4 times bigger than if the two charges are 2 centimeters apart. The first quantitative law of electricity was derived by Coulomb, and today Coulomb is honored by having his name used for the unit of electrical charge. A certain amount of electrical charge has been officially decided by the nations of the world to constitute 1 Coulomb of electricity.
Il secolo di Maxwell, l'Ottocento, si apre con una scoperta di straordinaria importanza per la storia dell'elettricità. Alessandro Volta, fisico dell'Università di Pavia, costruisce la sua celebre pila, il primo generatore statico di energia elettrica mai realizzato e il prototipo delle moderne batterie. L'invenzione di Volta deriva però dagli esperimenti di un grande scienziato bolognese a lui contemporaneo, Luigi Galvani, a cui si devono alcune preziose intuizioni sulla natura dell'elettricità animale e artificiale, che daranno i loro pieni frutti nei decenni successivi. Galvani, anatomista e fisiologo, nel 1791 pubblica un'opera, il Commentarius, in cui rivela una scoperta straordinaria. Ponendo una rana, decapitata e scuoiata, su una tavola in cui era collocata una macchina elettrostatica, ma senza alcun contatto con il conduttore della macchina, si potevano osservare delle contrazioni nei muscoli delle zampe. Lo stesso avveniva anche in assenza di generatore, toccando le zampe con un conduttore metallico scarico. Galvani interpreta il fenomeno ipotizzando l'esistenza di un'elettricità animale che si accumula nel corpo in vita e che, quando l'organismo è morto, si può scaricare attraverso le contrazioni osservate. E in un certo senso si avvicina alla verità. Oggi si sa che nelle cellule dei tessuti viventi c'è una differenza di potenziale tra interno ed esterno della membrana, e questo potenziale è alla base della trasmissione dei segnali nervosi. Volta però legge l'opera di Galvani, riproduce gli esperimenti e comprende che il fenomeno va spiegato diversamente. Per Volta le rane non sono generatori, ma solo rivelatori dell'elettricità che si produce dal contatto tra conduttori di specie diversa, in base alla tendenza del fluido elettrico ad espandersi e a tornare a una condizione iniziale di equilibrio. Fra i due scienziati nasce allora un'accesa controversia che coinvolge la comunità scientifica di tutta Europa, finché nel 1800 viene pubblicata la lettera di Volta in cui annuncia l'invenzione della pila, che basa il suo funzionamento sui fenomeni osservati. E dal dibattito nasce la prima grande invenzione del nuovo secolo.
Luigi Galvani was a scientist in Bologna, Italy, and he studied living creatures. He was an anatomist. He would cut open frogs and study their insides. He was also fascinated by electricity. He had an electrical machine. He would crank the machine and produce big sparks. And he noticed that when he made big sparks, that the frogs, nearby dead frogs on his table, that their muscles would twitch and their legs would move, caused by, apparently, electricity. And so he began to investigate the electrical properties of nerves and muscles that he believed in. He investigated what he called animal electricity. And what he did, one experiment, which is I would have loved to see, he took a bunch of dead frogs and he hung them on iron hooks outside his house during a thunderstorm. And a thunderstorm is an electrical phenomena, and these dead frogs would dance in the rain and the wind and the storm and the thunder. You would see these dead frogs dancing because they would be electrically stimulated. An example of animal electricity. His most crucial experiment, he would take a scalpel and connect it to the crural nerve, the leg nerve of a severed leg of a frog. He did lots of experiments on frogs. In fact, he used up so many frogs that there was a crisis in the locally. People couldn't buy frogs for dinner because he was cutting them open. He cut open this muscle of the frog, and this severed leg of the frog would move. And he used this as a demonstration of animal electricity. Now, the story diverges at this point in two different directions. He had a nephew called Aldini, and Aldini realized that he could become quite famous by making use of his uncle's idea. So he went to England and he arranged demonstrations, public expositions of the mysteries, the magic of electricity. He brought his electrical generator. He told them to supply him with a corpse of a recently executed felon. So you imagine there's a room full of people watching Mr. Aldini, and on the table is this corpse. He connects the electrical device to the neck of the corpse, and the arms of the corpse move, and the legs swing up and down, and the corpse has been brought back to life by the magic of electricity. And he gave this demonstration at many different places in England. He became very famous. He didn't really do any science. He just played with electricity. He inspired literature. This idea of a scientist bringing a dead person back to life inspired the wife of Percy Bysshe Shelley, the poet, to write that famous story, Frankenstein, where a scientist patches together the pieces of corpses and uses electricity to bring it back to life. And it's a very, very important story in the history of literature and in the history of science. But let's go back to Italy, to Como, to another city in Italy, where we had the scientist Alessandro Volta, also studied electricity. And he disagreed completely with Galvani, both politically and scientifically. Galvani did not favor Napoleon's creation of a puppet empire in Italy, whereas Volta regarded Napoleon as a great hero. Volta also did not believe in animal electricity. He realized that the effect of the scalpel on the muscle of the frog had nothing to do with electricity within the frog. The electricity was produced by the scalpel because the scalpel was made of two different kinds of metal. Volta realized that if you put two different kinds of metal together, like copper and tin or whatever, you will produce an electrical effect. And by making a multi-layered structure of coins, copper coins, zinc coins, copper coins, zinc coins, with wet paper between them, he could make a battery that produced an electrical current. Alessandro Volta invented the electric battery. He became a great hero. He was received by Napoleon, who said that he greatly respected the sciences, said Napoleon, that he would have become a scientist, except that he found another calling. And had he become a scientist, Napoleon, he would surely have been a great scientist. And he gave a big medal to Mr. Volta and a lifelong pension. And then he commanded that the French should build a large battery to do scientific research. The English heard about that, and they built a large battery too, and I'll tell you about that in a moment. Galvani and Volta have entered the popular literature in many different ways, the language, because Galvani, he didn't develop the device, but the device was named after him. The galvanometer is a very sensitive device that can detect very tiny electrical currents. I think it was discovered by Ampere later on, but it was named after Galvani. Furthermore, to galvanize, a galvanized iron pail is one made of iron that has been coated with tin. And that process of coating things with tin or zinc is called galvanization. And it developed after Galvani, but was named after him. My brother was a doctor, a physician, and he also collected some ancient medical instruments, and he had an electrical box, which was once used maybe in the early 20th century to treat patients, and it had a switch on it. It had two locations, galvanic or voltaic. You could treat the patient with either of two kinds of electricity, galvanic or voltaic. So Volta, too, entered the language, and more impressively, the basic unit of electrical pressure or electrical intensity is called the volt, after Volta. And the battery, for many years, was called the voltaic pile in many languages. So these people have not only taught us a great deal about electricity, but they have also affected our language. The discovery of the electric battery had a dramatic effect upon all of science. on biology, chemistry, and physics. Let me just give a couple of examples. A tremendous race took place between the French and the English to build the world's biggest battery. This was the beginning of big science, expensive science. And the biggest battery was built by the English. Humphrey Davy was a young scientist who believed that the battery would be a very powerful instrument in chemistry. It had been used by others to electrolyze water, to separate water, to decompose water into hydrogen and oxygen, to show that water is not a simple substance, but a compound of hydrogen and oxygen. And Davy went on to use the electric battery to produce chemical elements that had never before been seen in isolation. These were sodium and potassium produced electrolytically. Things like that were happening in England. Throughout Europe, people were using batteries to discover new things, to produce light, for example. Batteries were used to produce the arc light, which meant that people could have theatrical performances at night illuminated with intense light. Before that, if you went to a Shakespeare play, either you went in the daytime or you went at night in a dimly lit room filled with candles. Finally, we had the limelight. In any case, it was a tremendous development to have a reliable source of electricity where you could study different electrical phenomena.
Tra i grandi scienziati che segnano il cammino verso l'elettromagnetismo di Maxwell, un posto di rilievo spetta ad André-Marie Ampère, vissuto a cavallo tra il Settecento e l'Ottocento. Ampère nasce nel 1775 vicino a Lione, da una famiglia di piccoli commercianti. Della sua istruzione se ne occupa personalmente il padre, che lo istruisce in vari campi del sapere. Con la morte del padre, giustiziato dalla Convenzione a Lione nel 1793, la famiglia viene a trovarsi in gravi difficoltà economiche e Ampère deve iniziare a lavorare come insegnante privato a Lione. Ma non trascura la ricerca in campo matematico, dedicandosi al calcolo delle probabilità e alla teoria del gioco. Questi studi lo rendono noto negli ambienti scientifici, procurandogli una cattedra al Collegio di Lione e più tardi, nel 1805, alla Scuola Politecnica di Parigi. Qui prosegue le sue ricerche in matematica e chimica, arrivando a scoprire la legge di Avogadro qualche anno prima dello scienziato italiano, ma senza pubblicarla. Dal 1820 Ampère comincia a occuparsi dell'interazione tra correnti e campi magnetici, giungendo a fondamentali scoperte nel campo dell'elettrodinamica, di cui è giustamente considerato il fondatore. Maxwell lo definisce il Newton dell'elettricità. Le sue scoperte sono esposte nelle celebri memorie del 1826, sulla teoria matematica dei fenomeni elettrodinamici dedotta unicamente dall'esperienza, dove formula anche l'ipotesi dell'origine elettrica del magnetismo. In suo onore, l'unità di misura dell'intensità di corrente elettrica è chiamata ampere.
And the next part of our story took place in a classroom in Copenhagen in Denmark. And the teacher was Hans Christian Ørsted, a Danish professor of physics, whose best friend was Hans Christian Andersen. Hans Christian Andersen wrote fairy tales for children, sort of evil fairy tales, very cruel things that would happen that were appropriate for young children. Anyway, they were good friends with one another, and Hans Christian Andersen referred to Hans Christian Ørsted as Hans Christian the Great, because he was doing great things in science. He was teaching a course in what at the time was advanced physics. He was explaining how, if you have a voltaic battery producing a current, and you send the current through a thin wire, and he was giving this lecture in the year 1820, the thin wire would become hot. It was well known, and he was demonstrating this well-known effect. It would even glow and become red hot. But as he was making this demonstration, a couple of the students in the class said, "Professor, look." And he looked, and he saw that the current passing through the wire caused compass needles to move, and they would line up around the wire. Electrical currents produced magnetic effects. This was in my mind, the most dramatic discovery of the early 19th century. It was the early 19th century. It was a proof, a demonstration that there's a relationship between electricity and magnetism. Before that, it was just an analogy. Electrical things could produce forces, magnetic things could produce forces. Perhaps there was a mysterious, impalpable electrical fluid and another invisible magnetic fluid. But now it was realized that electricity and magnetism are deeply, profoundly related to one another. That electricity could make magnetism. He studied this effect, Ørsted did. He found that if you have a wire, a straight wire, going like this, and you put a current through it, that the magnetic effects would make circles around the wire. That is, that the compass needles would arrange themselves to point along tangents to the circle. If you have a wire going through the table and put a bunch of compasses around the wire is carrying a current, the compass needles will individually put together form a circle around the wire. The magnetic effect forms circles. And he wrote this up. He showed that the magnetic effect can go through wood and other materials, pass through materials, that it didn't depend on the nature of the wire. It only depended on the strength of the current going through the wire. He wrote a paper in Latin and sent it in the way scientists do today, except we don't use Latin anymore. The paper was translated by a young and not very famous French scientist whose name was Jean Ampère. And Ampère realized that the experiment was very important. He duplicated the experiment. It was very easy to do. I could do it myself. I did it as a 10-year-old child. It was easy together with batteries and wires and compasses. And he demonstrated it in Geneva to a group of French physicists, and he himself became extraordinarily interested in what he named electromagnetism, the unified relation between electricity and magnetism. And he studied magnetic effects. He showed he analyzed in detail the magnetic forces produced by magnetism. He invented the electromagnet, by which you could turn on the electricity and produce a magnet, and then turn off the electricity and the magnet would disappear. He realized that magnetism not only can be made by electricity, but he argued is always made by electricity. And he argued that a magnet, heretofore a mysterious object, had within it little currents inside that were producing the magnetism, the magnetic effects. And in a sense, he was right about that. He created a theory of what he called electromagnetism. He did for magnetism what Coulomb had done for electricity, just as Coulomb showed how charges produce electrical effects, and Coulomb showed how to calculate these electrical effects from a given distribution of charges. Ampere showed how a distribution of electrical currents produced magnetic effects and produced the mathematical equation describing how magnetic effects are produced by electrical currents. So charges, electrical charges, make electrical effects, electrical currents, which would soon be realized to be moving electrical charges, charges in motion, produce magnetic effects. The result, electromagnetism.
La teoria dell'elettromagnetismo sorge sulla base delle scoperte di un altro grande scienziato inglese, Michael Faraday, nato a Newington nel 1791. Faraday comincia interessandosi di chimica e pubblicando un primo articolo scientifico nel 1816, grazie a cui diventa membro della Royal Society. Le sue ricerche lo portano a ottenere il primo caso di liquefazione di un gas usando il cloro. Nel 1820 comincia anche lui, come Ampère in Francia, ad appassionarsi allo studio dei fenomeni elettrici e in particolare agli effetti meccanici dei magneti sui conduttori percorsi da correnti. Nel 1831 scopre il fenomeno dell'induzione elettromagnetica e dimostra che le correnti elettriche possono essere prodotte da magneti in movimento, così come da altre correnti variabili. Per spiegare questi fenomeni, postula l'esistenza delle linee di forza, come materializzazione dell'azione che magneti o fili percorsi da correnti esercitano sullo spazio circostante. La formulazione completa della teoria delle linee di forza richiede molti anni e viene esposta nel 1852 nel saggio Sul carattere fisico delle linee di forza. Un testo che rappresenterà per Maxwell la base per lo sviluppo della sua teoria dell'elettromagnetismo. Con la scoperta dell'induzione elettromagnetica, inoltre, Faraday apre la strada alla trasformazione dell'energia meccanica in energia elettrica e viceversa. Una scoperta di straordinaria portata per le possibili applicazioni tecniche. La dinamo, gli alternatori e i motori elettrici sono infatti una sua diretta derivazione. In suo onore, infine, è chiamata Farad l'unità di misura della capacità elettrica.
Well, science is a very international discipline. We've noticed that there have been major contributions from the English and the French and the Danish and the Italians. And now we move back to England, where we will talk about the work of Faraday. Now, Faraday was a young protege of Humphrey Davy. We mentioned Humphrey Davy. Humphrey Davy used the Italian discovery of the battery to produce sodium and potassium. He took Faraday as a young apprentice on a trip through France during the times of the Napoleonic Wars. And during those trips, they discovered the new element iodine, and they also showed that electrical fish, electrical eels, eels that produce shocks, are indeed electrical creatures and produce electricity. And gradually, Faraday became a very serious scientist, and he studied electricity and magnetism. And together, Davy and Faraday produced the world's first electric motors. Simple, what are called homopolar electric motors, were first developed by Faraday. Faraday then studied the process of electrolysis, and he discovered the underlying laws governing electrolysis, and in the process identified a fundamental unit of electricity, the amount of electricity that could extract technically one mole of a chemical element from solution. The laws of electrolysis are studied by all students of chemistry or physics, and they were developed by Mr. Faraday. But much more important than that, Faraday, knowing that electricity could produce magnetism, he knew about Ørsted's work on how electricity can produce magnetism, came to the conclusion that surely it must be possible that magnetism can produce electricity, the other way around. And so he investigated this possibility. What he did is he took an iron ring. This is a classic experiment done by Faraday, in which Faraday made a spectacular discovery, wrapped a wire around one side of the ring and another wire around the other side of the ring, connected one coil to a source of electricity, to a battery, and connected the other coil to a galvanometer. And the idea would be that the electricity on this coil would make magnetism. The magnetism would go through the iron ring and to the other side, and then would produce electricity on the other side. So he turned the switch, and nothing happened. He looked at the galvanometer, nothing was happening. The wire was getting hot because electricity was going through it, magnetism was being made, but nothing was happening. And then he turned it off. But then he turned it on and turned it off again because he noticed something very strange. And noticing this was very important. This was crucial. Scientists have to have an eye open for things they don't expect. Because yes, the galvanometer did move, but only when the switch was opened or closed. Just transiently, for a moment. When he would close the switch, there would be a pulse of electricity. When he would open the switch, there would be a pulse of electricity. What he discovered is not that magnetism makes electricity. Changing magnetism makes electricity. And that was the discovery of the law of magnetic induction. And Faraday would give many public talks about this law, and he would be asked questions from the audience. The person, a woman carrying a young baby, would say to him, Mr. Faraday, you've told us about your wonderful law, but what good is it? Of what use is your law? And Faraday looked at the woman and pointed at the baby and said, what's the purpose of your baby? At another time, another woman asked him, well, a lot of women would go to his lectures because he was a very charming man, and asked him again, of what use is your idea? And he said to her, she didn't have a baby, so he had to think of something else to say. He said, I don't know what use my idea will have, but I know that the British will tax, the government will tax it sooner or later. And indeed they did. The importance of his idea was this. Because magnetism makes electricity, because moving magnetism, changing magnetism makes electricity, by moving magnets, we can produce electricity. So we had a way of converting mechanical energy, such as could be produced at a steam engine, into electrical energy. And what works one way works the other way. We could convert electrical energy into mechanical energy. So we could produce energy at one place, electricity, ship it on wires to someplace else, and then convert it back into mechanical energy. We could have factories powered by electricity. We could have electric lights powered by electricity. We could have, he began the age of electricity, the second industrial revolution, the industrial revolution powered by electricity. The first one was powered by steam engines, was made possible by the work of Faraday. Now, not only that, not only was his work practical, but he set the stage for the next developments in the science of electromagnetism. He addressed a philosophical question that had been around for a long time, and that was how are forces transmitted? We all know about gravity. The gravity of the sun comes to the earth and affects the motion of the earth. How do we have action at a distance? How can the sun, which is so far away, affect the earth? Or how can a charged body affect another charged body separated from it? How do we get action at a distance? And what Faraday suggested, both for gravity and for electricity, for gravity, that the sun produces a gravitational field everywhere in space. And it is that gravitational field, not the sun, that causes the earth to move. And similarly, a charged object produces an electrical field everywhere in space. And it is that electrical field that acts upon other charges. So he produced this notion of an electrical field and a magnetic field, and those were the keys to the development of today's theory of electromagnetic forces, of electrical fields and magnetic fields.
James Clerk Maxwell nasce a Edimburgo nel 1831 e cresce nella campagna scozzese. Fin da bambino mostra un vivo interesse per il funzionamento degli oggetti che lo circondano e notevole intuizione per i meccanismi, dal semplice giocattolo alla macchina a vapore. Fino a 13 anni viene educato in casa, poi inviato alla Edinburgh Academy. Già durante gli anni di studio all'Academy, Maxwell, 14enne, scrive un articolo sulle curve ovali, cioè ellissi e curve a più fuochi, che viene presentato alla Royal Society di Edimburgo. All'Università di Edimburgo e in seguito al prestigioso Trinity College di Cambridge, Maxwell si dedica intensamente agli studi scientifici, senza tralasciare i suoi interessi anche nel campo religioso e filosofico. Maxwell, infatti, non smetterà mai di interessarsi ai problemi religiosi, rimanendo convinto che scienza e religione potessero e dovessero conciliarsi tra loro. Dopo la laurea comincia a insegnare e a pubblicare contributi scientifici che ne rivelano le grandi capacità in ambito fisico. Il più grandioso risultato delle sue ricerche sarà però Electricity and Magnetism, pubblicato nel 1873, in cui Maxwell presenta le 4 equazioni che portano il suo nome e che rappresentano uno dei punti più alti della matematica e della fisica del XIX secolo. Riconosciuto da allora padre dell'elettromagnetismo, continua a lavorare fino agli ultimi giorni della sua vita. Muore a Cambridge il 5 novembre 1879.
We're back to England for the next stage of our story, the synthesis of everything that had happened before, that was carried out by one of the greatest scientists ever, James Clerk Maxwell. Maxwell is the man that invented Maxwell's equations. Maxwell's equations are the equations that appear on the T-shirts of physicists the world over, usually in day-glow colors. People who are proud of being physicists will demonstrate their pride with Maxwell's beautiful equations. Maxwell was aware of the work that had been done by Coulomb, the work that had been done by Oersted, by Ampere, and of course Faraday, and he assembled all of these together in the form of what are called differential equations, partial differential equations, a very convenient form of mathematical equation that embodied the empirical laws that had been developed by others. 4 different equations, well, there were actually more than 4, there are sort of like 12 or maybe more as originally written down, but the equations that embodied all of the experiments that had been done before. Well, he wrote them down. He wrote down these today 4 equations, plus one more, and the other equation had to do with electric charge. It said that electric charge could not be created or destroyed. You can't just make a positive electric charge. You can only make a positive electric charge if you also make a negative electric charge, in the same way that you can't make a north magnetic pole without making a south magnetic pole. Electric charge was conserved. But the equations were incompatible with conservation of charge. They didn't make sense. They were contradictory. Something was very wrong. So Maxwell had to change the equations. He had to add something for which there was no experimental evidence at that time, a new term. He called it the displacement current. It doesn't matter what it's called. But by putting in that additional term, the equations became mathematically consistent with one another. And Maxwell was very happy. But then he realized that these equations, so modified, described not only electricity and magnetism and the relation between electricity and magnetism, but they described electromagnetic waves. Now, at this point, we have to begin to talk about light, because these waves that came out of the theory of electricity and magnetism, electromagnetic waves, he could calculate their velocity. He could theoretically deduce how fast they would travel through air or through the vacuum. And he found that the speed of these waves was exactly equal to the speed of light that had just recently been measured with great precision. And he got the same answer. And therefore, he concluded that what he was seeing, what he had deduced, was light, that light is an electromagnetic phenomena. Light is not a stream of particles. Light is not some hypothetical wave of unknown nature. It was simply made of electricity and magnetism.
Con la teoria dell'elettromagnetismo, Maxwell spiegava anche la natura della luce. Descritta come una radiazione elettromagnetica con lunghezze d'onda diverse, in uno spettro che va dal rosso al violetto. Il suo lavoro, così, proseguiva quello di Newton ed Eulero, mentre nello stesso secolo diverse menti si preoccupavano di determinare l'esatta velocità dell'onda luminosa. Il francese Jean-Bernard Léon Foucault, a metà dell'Ottocento, aveva compiuto esperimenti con uno specchio girevole e scoperto che la velocità di propagazione della luce varia in relazione all'indice di rifrazione del mezzo nel quale si propaga. Ad esempio, è maggiore nell'aria che nell'acqua. Negli stessi anni, la luce elettrica arrivava nelle strade d'America con l'invenzione della lampadina. Un oggetto rivoluzionario creato da Thomas Edison nel suo laboratorio di Menlo Park nel New Jersey, dove aveva provato che per produrre illuminazione con l'energia elettrica i migliori materiali risultavano filamenti di bambù oppure il normale filo per cucire carbonizzato. Questi filamenti venivano inseriti in un bulbo di vetro in cui si produceva il vuoto per impedire la combustione dei filamenti incandescenti. La notte di San Silvestro del 1879, Edison illuminò la strada principale di Menlo Park, di fronte a migliaia di abitanti pieni di meraviglia.
Galileo, going back a long way to the early 1600s, was able to estimate the speed of sound, because sound really doesn't travel too fast. It travels only about 300 meters per second. And he was able to measure it. He also tried to measure the speed of light, but he failed. And he failed for a very good reason, because the speed of light is about 1,000,000 times faster than the speed of sound. So Galileo gave up. He said, look, I've measured the speed of sound. Let somebody else measure the speed of light. Then we come to Newton. Newton was born in the year that Galileo died. So he is very much a logical successor to Galileo. Newton studied the motion of the planets. We all know about that. But he also studied light. And he was the first person to separate light into the colors of the rainbow. He showed that sunlight passing through a prism is split up into the colors, and he defined the 7 colors, 7 primary colors of light, which are red, orange, yellow, green, blue, indigo, and violet. And every time I mention that to students, the students will say, what's indigo? I don't know what indigo is. It seems to me there are only 6 colors, but he had 7. And the reason that Newton had 7 colors is because there are 7 notes in the scale, do, re, mi, fa, sol, la, ti, or C, D, F, G, A, B. 7 notes in the scale, 7 colors. There was something wave-like about light. But nonetheless, Newton insisted that light is made of particles. And so it was believed from Newton's time until approximately 1850. Newton had to be able to explain the various properties of light in terms of light as particles. Why did he believe light is particles rather than waves? Because if you have a bent tube, for example, and you talk into one side of the tube, you can hear it at the other end of the tube. The sound passes through the bent tube. But if you shine a light in one side, put a candle by one side of the tube, or let some sunlight enter one side of the tube, it doesn't make it around the corner. So sound is a wave, and light is particles. He was able to calculate, Newton was, the speed of sound through air in terms of the pressure and the density of air, but he could not calculate the speed of light. He knew the speed of light. A Danish scientist, Ole Rømer, had deduced roughly the speed of light from observations of the moon, of the innermost moon of Jupiter, Io, the innermost moon of Jupiter. So the speed of light was known. It was known to be 1,000,000 times faster than sound. But it consisted of particles, not waves, according to Newton. Newton had to explain reflection, but that's easy. Billiard balls bounce off the rail of a billiard table, so also the particles of light bounce off a mirror. That's easy. In fact, Newton was so smart that he invented a new kind of telescope based on a mirror, the reflecting telescope, and that was the telescope that made possible the great discoveries in astronomy that would happen soon thereafter. But he had to explain refraction, the bending of light when it enters glass or water. And the way he did that was to invent a new force. Newton realized that it pays to invent a new force. Remember, he invented the force of gravity, and that allowed him to understand how things fall on Earth, how apples fall, and how planets go around the sun, and how the moon goes around the Earth. All that from one force. So therefore, he invented another force, which is the force between particles of matter and particles of light. And that force would cause light to travel faster in water, for example, than in air, and thereby explain the bending of light as it entered water or glass. And so he explained refraction in terms of his brilliant theory of light as particles, which everyone believed, until a certain Frenchman enters the game. His name is Foucault. And I mention Foucault because you might be familiar with him. If you go to a science museum, you'll see Foucault's pendulum. You'll see a pendulum that swings back and forth, and as the day goes on, the plane in which the pendulum is moving rotates. And that was the first demonstration, proof, if you will, that the Earth is spinning about its own axis. So Foucault was very famous in France for being the first person to demonstrate physically that the Earth is spinning. But he also measured the speed of light in water, and he found that light moves more slowly, 3/4 the speed in water that it travels in air, opposite to what Newton had said. From that point on, in 1850, Newton's theory of light was dead. Everyone agreed that light was a wave. And then came Maxwell, who showed it is an electromagnetic wave. Light is an electromagnetic wave. In 1800, other kinds of light had been discovered. Infrared light, which is light with a longer wavelength than red light, and ultraviolet light, which is light with a shorter wavelength than visible light. So there are many different kinds of electromagnetic radiation. There was a spectrum of electromagnetic radiation. Scientists began to wonder whether it could be that we could artificially produce much lower frequency, longer wavelengths of electrical radiation, what we today call radio waves. And now the scene moves to Germany, to a physicist named Hertz, who was the first person to connect together various electrical devices to make electromagnetic waves. Not light waves, not ultraviolet, not infrared, but real long waves called radio waves. And he sent these waves from one side of the room, his laboratory, to the other, to a detector at the other side of the room. And therefore had proven directly that there were electromagnetic waves, that you could make them in the laboratory directly, electrically, following the laws of Maxwell. Well, that leads us to a young Italian physicist named Marconi, who realized that Hertz's discovery could be of the greatest importance to society, because surely it would be possible to send these waves further than just across the room. So he was able to send them. He developed a device, a generalization of what Hertz had done, and sent waves for a distance of a few kilometers. And then he sent waves across the English Channel. He sent them from England and received them in France. And then he was even more ambitious. He sent a message across the Atlantic from England to America using electromagnetic waves, radio waves. He discovered wireless telegraphy. He sent the message, but with dots and dashes, using some kind of code, such as the code that would later be invented by Morse, the Morse code. And he realized that information could now be sent from one continent to another. In the old days, before his discovery, the newspaper you would read in New York told you what happened in London 2 months ago. But now you could learn what happened in London today. So this was a revolutionary development. It meant that ships crossing the Atlantic were no longer isolated from the world. They could communicate, they could send messages home, for example, explaining that they were in trouble with SOS, or they could simply write to their friends send messages to their friends at home saying, we'll be landing in 2 more days, meet me. It was a remarkable discovery, a very important discovery. Happened around the turn of the century, around 1900 and 1905. Wireless telegraphy became extremely important very quickly. Somebody very smart in Pittsburgh, Pennsylvania, developed the first commercial radio station, KDKA, broadcasting from Pittsburgh, giving advertisements and playing music to people with little primitive radio sets and earphones who could listen to the music and buy the product. A few years later, 1948, I had my first television set. And that was the beginning of the electronic revolution. You know what has happened since. Our American youth seems to be thoroughly plugged in, and I'm sure that's true in Italy and other countries as well. There doesn't exist a teenager without wires coming out of his ears. So the 20th century began the age of electricity and electronics. We are so much dependent upon the discoveries of Maxwell and Faraday and Coulomb and all those others. Just think of how dependent we are upon electricity. Edison invented the light bulb, and today our homes are not lit by candlelight or gaslight, but they're lit by electricity. Alexander Graham Bell invented the telephone. And where would we be without the telephone? We depend on the telephone. Today, of course, today's telephones are not even connected to wires. They're cell phones or mobile phones. And where would we be without mobile phones? Today, if I'm driving a car, I wouldn't be caught without having a phone with me, because I might have a flat tire, or I might decide to visit a friend and let him know, her know that I'm coming, or I might decide to make a reservation at a restaurant, and without the phone, you're nobody. Elevators. You couldn't have skyscrapers or tall buildings, or even 10-story buildings without elevators, but most elevators depend upon electricity. People live in places which are virtually impossible to live in, like Texas. People live in Texas because they have air conditioners. Otherwise, it would be pretty difficult to live in Texas, or Saudi Arabia for that matter. If you want to live comfortably in Saudi Arabia, you would better have electricity to power your air conditioner. All of our technology is electrical. All of our computers are electrical. All of our society is electrical. And our electricity is made from coal, and our coal is making carbon dioxide, and that's leading to lots of problems that we don't have time to talk about now. But let me change the subject a little bit from technology to science. In the 20th century, at the end of the 19th century, the first elementary particle was found, the electron. The electron is the object that is responsible for electricity. It's electrons moving through wires that produce electrical currents. It soon became apparent that electrons are parts of atoms, and atoms are made of electrically charged nuclei surrounded by electrons. The structure of all matter is electrical. We are made of molecules, and those molecules are made of atoms, and those atoms and molecules and cells and organs are held together by electrical forces. We are electrical. Light is electrical. Matter is electrical. Everything is electromagnetic, with almost no exceptions.